And we move on to Fiona Porter. Fiona, are you here?
Yes, can you hear me?
Yes, we can hear you. Can you share your screen?
Yep. Okay, that's coming through okay?
Yeah.
Okay, grand. Well, hello everyone, and thanks to the organisers for giving me a chance to speak today. I'm Fiona Porter. I'm a final year PhD student at the University of Manchester, and I'm going to be talking about uncertainty quantification. So, as I'm sure you're all aware, machine learning is expected to be absolutely vital for large-scale surveys like those performed by the SKA, because there's simply going to be too much data for manual or even crowdsourced classification to be practical. While advancements like the widespread use of GPUs have allowed for increasingly deep and complex ML models to become viable, there remains the issue that it's entirely possible for a model to be both very confident and very wrong. Clearly, there's value in being able to quantify the uncertainty in the predictions of a classifier, and an understanding of whether a model's confidence is justified is needed to make sure that it's reliable. I'm going to be talking a lot about probability, so thought I'd clear this up early on. When I refer to predicted probability, I'm talking about the normalized outputs from the final fully connected layer of a convolutional neural network, which encodes the probability of an image belonging to each class the model can identify. Normally, the largest one of these is taken to be the image's predicted label, but this method doesn't distinguish between an image which is labeled as a particular class with 51% probability and one that's labeled with 99% probability. Looking into these distinctions will be important for quantifying uncertainty. So to start with, let's define the uncertainty we'll be talking about. Uncertainty within the machine learning models can be broadly separated into two varieties, aleatoric and epistemic. Aleatoric uncertainty arises from features within individual images of sources that make them more difficult to identify. Sometimes these features might be removable, for example, some background sources, but sometimes an object will just have an unusual morphology, which will confuse even human experts. While sometimes a higher resolution image will give a bit more clarity, because aleatoric uncertainty derives from inherent properties of the source, it's impossible to entirely eliminate. Epistemic uncertainty, on the other hand, is uncertainty within the model itself that arises from it having a limited ability to make predictions with confidence. As the training set can't represent every variation within a population of objects, the model has a limited quantity of information to use to make its predictions, and thus it will always have some degree of uncertainty in any prediction it makes. For sources that are significantly different from its training set, the model's uncertainty can become very high and its predictions extremely unreliable. This uncertainty can be minimized by ensuring the training set is as large and as representative of the general population as possible. Speaking of training sets, the dataset I've used for this work is one of Fanaroff-Riley galaxies. For some astronomical context, the Fanaroff-Riley scheme is a way to classify radio-loud AGN and has two main classes, FR1 and FR2. While both have characteristic radio jets, they have noticeably different morphologies, as you can see. It's believed that the same underlying mechanism creates both types of galaxies, with the difference between them being caused largely by the surrounding intergalactic medium. So the FR classification scheme is useful for learning about the region around an AGN. The MIRABEST dataset is a batch dataset of FR galaxies derived from the catalogue presented in Miragai and Best 2017, with images created using data from the VLA First survey and can be accessed on Zenodo at the link at the bottom of the slide. In addition to images having an FR class, they're also tagged as being either confidently or uncertainly classified as FR1 or FR2, as judged by the paper's authors. The network architecture used for this model is a modified variant of LeNet. It uses the same basic structure as standard LeNet, with the addition of a spectral normalization to regularize latent space, plus a dropout layer immediately before the final fully connected layer. The dropout layer allows for Bayesian approximation of the predictions when turned on, which is used to calculate some of the uncertainty metrics I'll be evaluating. For this work, I trained two models. One that was trained using all images, whether they were confidently or uncertainly classified, and one which only used confidently labeled images. I'll refer to these as the full model and the confident model, respectively. On to uncertainty metrics. Entropy is a measure of the model's predictive uncertainty, how highly it ranks one label above another. It can be calculated for any image with a single pass through the trained network as the sum of negative p log p, where p is the predicted probability for each class. Obviously, this is minimized when the probability for one class is 1 and for all others is 0. I'll be using a slight variation on this calculation, which also gives an insight into the consistency of the network's predictions by finding the predicted probabilities for multiple different dropout configurations and taking the average. This version is minimized when the predicted probability for one class is 1 for every dropout configuration. Now, mutual information, which is a measure of model uncertainty. That is, how confident the model is that its predicted probabilities are correct. It's also calculated using an ensemble of predicted probabilities for different dropout configurations and is the difference between the entropy and the expectation value of the entropy. To highlight the difference between these two measures, here's an example. For a binary classifier, if an image's label is 50% of the time class A and 50% class B, but the predicted probability for that class is 1 every time, both entropy and mutual information will be maximized. The model's predictions vary significantly, so it's both uncertain of the correct class and uncertain about the accuracy of its predictions. If every prediction, however, gives a probability of 0.5 for both classes, the model is still uncertain of the correct class, but it's very confident that it doesn't know. It has high entropy, but low mutual information. This makes mutual information a way to quantify epistemic uncertainty. Now, a metric that uses logits probability. The logits output from a neural net are non-normalized and can consequently be plotted as distributions in latent space. If a network is well trained, we expect each class to form a separate cluster. We assume these distributions are multivariate Gaussians and fit them as clusters using a Gaussian mixture model. This shows the model's epistemic uncertainty by examining the density of sources in latent space. In regions of latent space which are densely populated, the model has a large quantity of information about the sources, so it has low epistemic uncertainty. Sparsely populated regions represent sources the model has limited information about and have high epistemic uncertainty. With all that explained, on to some results. We see a wide range of entropy values for different images in the MirrorBest dataset, regardless of model. There are some sources the model is extremely confident of, with near 0 entropy, and some it's very unsure of, nearing the maximum entropy value of around 0.7. We can see that a higher proportion of uncertain images have high entropy compared to confident images, regardless of whether or not the model's training set included them. We can also see there are somewhat more very low entropy sources for the confident model and noticeably more very high entropy sources for the full model. Intuitively, this might make you think that training on only confident sources might produce a better classifier, but let's look at how these histograms break down in terms of images being labeled correctly. What you can now see is that for the full model, the number of incorrectly labeled sources is very, very low in the lowest entropy bin, and the proportion of incorrectly labeled sources remains low until the 2 highest entropy bins. By comparison, there's a noticeable portion of incorrectly labeled uncertain sources for the confident model at lowest entropy, which continues throughout the other entropy bins. This suggests that by only training on confident sources, the model itself has become too confident about its ability to predict accurately. It doesn't know what it has limited information about, and its epistemic uncertainty has worsened. We can also see this looking at the mutual information. In the full model, the highest mutual information values are exclusively found in the highest entropy bin, while for the confident model, high mutual information is seen for noticeably lower entropy. Since mutual information is a measure of epistemic uncertainty, this suggests fairly plainly that by failing to expose a model to messy images, which likely have high aleatoric uncertainty, your model will be overconfident in its predictions and have a higher epistemic uncertainty on the whole. Now, clustering. These are the clusters produced by the GMM fitting for the images in MirrorBest. As you can see, they do broadly separate into 2 class clusters, with FR2 on the top left and FR1 on the bottom right, but there's a definite region of overlap. This corresponds to images where the model's predicted probabilities for both classes are fairly similar. it thinks they could conceivably be either class. If we take a look at what images from different parts of the clusters look like, we can see some trends. Far away from the overlap region, we see that the sources tend to be quite characteristic of their class, even when feature space is relatively sparse. In the overlap region, however, the images found there tend to be somewhat visually ambiguous, with a higher population of uncertain sources. So what does this mean? The source entropy is noticeably higher in this overlap region than it is for either the sources at the cluster centers or the outliers at the far ends of the distributions, suggesting that entropy here is serving as a good indicator of aleatoric uncertainty. As might be expected, mutual information is also higher in this region. The model is both unsure how to classify the sources and unsure how accurate its predictions might be. Entropy and mutual information are good markers of a classification being unreliable elsewhere too. The source highlighted in the upper right of the plot has high predicted probability, but also high entropy and very high mutual information. So it's something that's fairly easy to pick out as potentially misclassified. So, in conclusion, being able to quantify uncertainty in ML models is valuable when trying to determine how much to trust their predictions. We can see that models can benefit from the presence of messy data in terms of epistemic uncertainty and caution against highly curated datasets. Generally, machine learning models and humans find the same images difficult to identify, and aleatoric uncertainty reflects an image's messiness. And finally, examining data in latent space can help us spot images that the model might struggle with and allowing us to flag them for human intervention. And that's all from me. Thanks very much.
Thanks, Fiona, for this excellent talk. Are there questions for Fiona in the audience here? I don't see hand raised. Do we have questions on Slack? Yeah, I fear it's running late. Everyone is tired. Thanks again, Fiona, for this excellent talk.
Thank you.